Morning, folks. Hope you're doing all right. I have to say, generally, I'm very surprised that this computer is handling any of this okay, because I think it's 7 years old. And I mean, recording video, sending video. Yeah, I should knock on wood or something. Okay, whatever. 9, 8, 7, 6, 5. Yeah. All right. Okay, welcome back. I hope your day is going okay. Let us just do a round of announcements. I think the key one is because it is a Tuesday. Just a reminder, there's that online quiz, so please get that turned in sometime during the day today. It's meant to be just like in class, a short quiz. And stick with the web work. That's still happening. Office hours are there. I did send an email yesterday just to make sure. I'm just trying to make sure that everybody stays as connected as possible. I know things are all different, so yeah. And if you ever need, there's an office hour by appointment as well. So today we are going to do one thing as a warm up here because we're going to need this idea 2 slides from now. You've got 2 points here. The first point is x1 comma y, and the next point is x2 comma y, and you'll notice that both points have the same y coordinate. So that's intentional. These 2 points have the same y coordinate, but maybe not the same x coordinate. So that's why there's an x sub 1 and an x sub 2. So what is a formula for the distance between these 2 points? We should draw a little picture. X-axis, y-axis. So both points share the same y coordinate, meaning they're at the same height. Right, so one's not above the other, but like they're at the same level, same floor level. But these 2 points could have different x values. So maybe x1 there, x2 here. And I guess the question I'm trying to get at is, what would be a formula? I want you to stop and think about, like, if you were to connect this line segment together, what would be a formula that gets you how long is that line segment that was just drawn? And if you can come up with it directly, cool. But if you feel stuck, what if you just did something like, now I'm just adding to the story here, so we're going to remove this part of the story in a moment, but let's just pretend that the x coordinate there is a 3 and the x coordinate here is a 10. Well, then what would you say, right? If there's a 3 here and a 10 there, then how far away are these 2 points from each other when connected by direct straight line segments? I'll give you about 1 minute to think about that and come up with some ideas. Oh, great. Okay, so is this better? Thanks for that comment. hang on. Better? I did get a comment from one who couldn't hear me. Can everybody else hear? I'm looking in the chat, or just have somebody unmute to say. Come on, somebody's got to give me some feedback. Okay, you can hear. All right, so the student who had an issue left, and hopefully will be back, or will watch the recording. I'm sorry. Okay. Okay. All right. So, all right. Well, maybe we will see Brian back in a moment. Okay. So this. Sorry. Now I'm a little flustered. Okay. Just gotta move on. That's why this is recorded in part. Okay, so the distance between these two here, I hope you're seeing would be 7, or rather, I guess 10 minus 3, right? It wouldn't be 13. The thing is, I just made up these numbers 10 and 3. So what if we got rid of those numbers? Then we ought to be thinking like the distance should be x2 minus x sub 1, right? Or the key thing is it should be this bigger x value minus this smaller x value. And by the way, yeah, this comment here, okay, and he's back. I hope everybody else could hear, so just maybe you got to check some hardware settings. That would be my guess, like in addition to the software settings. Okay. So here okay. So does our formula work even if x1 and x2 are positive, negative? Is it going to work out? Does the formula still work in general of x2 minus x1? Do you have to, or in other words, do you have to do something different if one or both of the x values happens to be negative? And I'd say you don't have to actually do anything different. So I want to imagine the following scenario. Like I'm going to draw. So let's say this point 3, 8 for example, right? Like a point right there, and then the point 10 comma 8, just to make an example. We got this point there, and these two, like I want you to imagine it like we're looking from above, right? Like we're flying above, and we see like there's a construction worker here, and there's a construction worker at this other point, and connected between them, these two people are holding on to like a steel pole or something like this, 7 feet long then, right? Because one person's standing where x is 3, the other's standing where x is 10. And let's say that both of these people move 5 units to the left, so walking that way. So if this person at this left point here walks to the left, then ends up like right over here. Sorry, this 8 is kind of in the way, so this picture is not quite to scale, but should end up right there. Why where x is equal to -2? Well, if this person here starts at x equals 3 and walks 3 units to the left, ends up right here on the y-axis, but that's not a total of 5 units yet. Needs to walk 2 more units still, so that's why it ends up over here at x is equal to -2. The person who's standing where x is equal to 10, if that person also moves 5 units to the left, ends up somewhere in the middle here. 5 units to the left of 10 should be x is equal to 5. Okay, and then the point is, so if both construction workers here were to walk 5 units to the left, one is now at x equals -2, the other's at x equals 5, and what I have seen people do in the past is to then say, oh, 5 and -2, and then people do things like 5 plus -2, which would be a 5 minus 2, and get 3. And then my question would be, how did this steel pole, which was 7 feet long before, now magically shrink down to 3 feet just because both people walk the same distance to the left? Right? That wouldn't make any sense, right? So instead, we should get the same length for the pole. It should still be 7, and how you get that is you do 5 minus -2. So it's still the bigger x value minus the smaller x value, right? Still 5 minus -2, which ends up being 5 plus 2, which still is 7. So the point is you don't have to do anything different. In general, if you have 2 points, one point is x1 comma y, the other point is x2 comma y, meaning they share the same y coordinate. That's why it's a y in both spots. Then to get the distance, you should just do the bigger x value minus the smaller x value. Bigger x minus smaller x. And we won't go through this in detail, but you can imagine, no surprise, if you had a point x comma y1 and a point x comma y2, so the 2 points share the same x coordinate, you can imagine that the 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 formula should, so same x coordinate, now the formula for distance should be bigger y minus smaller y, right? That would, I think, seem to make sense here. We're doing okay volume wise, I hope, for the one who had an issue. Just, you can type if you'd like to. Okay, I'll look over there to see in a moment. So this bigger x minus smaller x business, the thing that we drew a picture of earlier, you've got a point there and a point there. So that distance right there, that goes by the name horizontal distance. It's a good name for it, right? Because we're talking about a horizontal line segment. And then this one over here, if it's a bigger y minus smaller y, so you've got a point, and then so the 2 points should have the same x coordinate, so they should be on the same vertical line here. So then this distance here is called a vertical distance, and I think, again, that I hopefully makes sense for the name of this. Okay, so these are two warm-up ideas, and what we're going to do is apply these to the next question over here. So I'd like to derive, and I don't mean differentiate. Okay, so sometimes students say the word derive and they're thinking about f prime. Here, I mean, derive means to get a new idea based on old ideas. So using the two older ideas we just saw, this vertical distance and horizontal distance, I'd like to get the general distance formula for 2 points. So the hint here is we're going to need the Pythagorean theorem. What I mean by the general distance formula is that the 2 points that we saw in our situations earlier either shared the same x coordinate or the same y coordinate. Now we're going to have 2 points where the 2 points don't have the same x coordinate, so different x coordinates here and here, and the 2 points don't have the same y coordinate either, right? So you'll notice that the 2 points are drawn at different heights because of the different y values, and then at different x values. We are looking for the distance between these 2 points. So if we connect this with a straight line segment, we'll just call that d for the distance that we're trying to find. Right? We're trying to find that distance right there. And now the question I want to ask is, do you see a right triangle in this picture somewhere? And every time I've run this experiment in class, I get people starting at first to go no, and then people are like, oh yeah, I see it. Or rather, there's two. There's one up here, maybe not the one that you saw because that D is sort of visually in the way, but there's another one down here. Both of these work, but I'm going to focus on the one that's down here. So if I just reveal the next slide over, we've got this, right? So in order to create this right triangle, we had to walk perfectly horizontally this way and perfectly vertically this way in order to create that right angle right there. So here's the thing. Then the question is, how long is this? How long is that? And then how long is this? But that's where talking about going perfectly horizontally and perfectly vertically is helpful, because we just talked about horizontal distance and vertical distance. So if it helps you out, first of all, this x, the information is already in the picture up here, but if you'd prefer, you can put a tick mark on the x-axis, call that x1. You can put an x2 here if you'd like to. And then those two, right, because this point here, the x2 value would go down there. And then these two pieces of info together tells you this horizontal distance right there. Should be a bigger x value minus smaller x value. Same deal, if you'd like to, you can take this this y value and put this on the y-axis. You don't have to if you don't want to, but the information's already in the picture. And then over here, y2. So then this distance right there, it should be the bigger y value minus the smaller y value. In other words, y2 minus y1, like that. If I advance the slide forward, you'll see this kind of cleaner. So now we have this right triangle, and we should apply the Pythagorean theorem, right? Remember, a squared plus b squared equals c squared. So it's our hypotenuse is rather nice. It's just d. The a is maybe this one, and the b is that one. So those are not as nice, but it's not too bad. We're just subtracting two numbers from each other. So normally we think a squared plus b squared equals c squared. I just swap the two sides. So d squared is what I chose to write first. You could swap the sides if you'd like of an equation. And then you've got a here squared, and then you have b here squared, right? So standard applying the Pythagorean theorem. And now here's the thing. We wanted, in the end, we wanted distance. We wanted d, not d squared. So we have d squared. How we're going to get d? We're going to need to square root both sides. So square rooting both sides, d is equal to plus or minus the square root of so what we had before. And then, yeah, I put this plus or minus sign here as a reminder because there's later times in the semester where this algebra comes up and people forget the plus or minus sign. However, in this specific situation, we're talking about d as a distance, so we can't have a distance like -5. So for this specific thing, we're going to remove that plus or minus sign because distance can't be negative. Okay, so this is the standard distance formula. It's a formula that students I know tend to kind of memorize and sort of forget part of the pieces of or something like that. I don't want that to happen. I want you to see that there's a connection with the Pythagorean theorem. So let me make a couple comments. I'm not trying to rant. I'm just trying to point out like there are things that people kind of memorize incorrectly. Like instead of a plus sign here, sometimes people put a minus sign. Instead of minus signs here, sometimes people accidentally put plus signs. So we should go back and talk about the reason there's a plus sign here is because of the Pythagorean theorem. A squared plus b squared equals c squared. That's that plus sign. Why are there minus signs here and there? So that's because of the vertical distance and the horizontal distance. And so in just the slides before, we had said that to get those distances, you do a bigger x value minus smaller x value or a bigger y minus smaller y. The squareds are here because when in the Pythagorean theorem you say a squared plus b squared. Finally, why is the square root sign here? It's because we had to undo the square that was up there. So in Pythagorean theorem again was a squared plus b squared equals c squared, emphasizing that squared. So all of the pieces have their place and their reason why they appear. I think what sometimes happens is people kind of memorize some of the things in different places than where they really actually truly belong. So I hope what you're hearing here is an explanation of why is there a plus sign where it is, why are there two minus signs, why are there two squares, and why is there a square root sign. The last thing I need to say about this before moving on is sometimes people do incorrect algebra and try to distribute the square root sign. You cannot distribute a square root sign if you've got a plus sign. So people try to distribute the square root sign and then further try to cancel the square root with the square. If you could have distributed the square root sign, fine, but that wasn't allowed. So this is as simplified as the formula gets. People often try to simplify this using poor algebra. That doesn't work out, and it doesn't simplify any further whether you plug in something or not. It's just, it looks like this. So this is the distance formula. You will need to know, where this formula, and we are going to apply this in the optimization problem we look at in just a moment. We have one other idea we need for the optimization problem we look at, which is I want to start with this list of numbers. And we're going to put the numbers in order. Then we're going to take the square root of each of the numbers. And then we have a new list of numbers. And so we'll take that new list of square rooted numbers and then we'll put those numbers in order. So, okay, how does this look? So let's see. So put the numbers in order. Well, first there's a 1. And then the next biggest is a 4. And then we've got a 9. And then a 16, and then a 25, and then a 36, and then a 49, and then 81, no, or 64, and then 81, and then 100, and 121, and 144. Now we've done that step. Now take the square root of each of the numbers. 1 is its own square root. When you square root 4, you get a 2. Square root 9, you get a 3. I think you're seeing the pattern of what's going on here once you've square rooted each of the numbers. Check. Now let's take the square rooted numbers. So now look at this list and then put them in order. And what do you notice? Is that we don't have to do any work to put these numbers in order, right? These numbers are already in order. Now I know this sounds silly, but the thing is the numbers were already put in order in step 1, and then the actual numbers we were looking at in step 3 were different because we square rooted, but they were already in order. I know this sounds strange, but if you have a bunch of numbers in order and then you do a process, depending on the process, the numbers that you have as a result might be in order or might not. There's no guarantee in general that the numbers you would have would be in order. However, for square rooting, things are fine. If you have numbers in order, then if you square root, that's not going to change the order. By that same reasoning, if you do the reverse process, you square all the numbers instead, then the order of the numbers won't change. This is an important idea because it leads to this, that in order to, if you're going to try to find the x that makes y small, or k small, or m small, or whatever, if you're trying to find the x that's going to make y small, if it's more convenient for you, then find the x that makes y squared small instead. Okay, so this is a very key idea. We're going to use this idea in just so the distance formula we talked about, and then this idea right here are going to both appear in the optimization problem we look at right now. So let's find the point on the curve y equals root x, which is closest to the point 16, 0. Now, this curve is one that, at least in my algebra class, students are expected to know what that curve looks like. But I'm going to remind you here that this is a sideways half parabola that looks like this, roughly speaking. We got this point 16, 0. Maybe it's like right over there. That would be that point. And I'll just to talk about, like, the thing is, this point over here on the parabola is probably too far away. I mean, this point over here is probably too far away. The point we're probably looking for is probably that point. That's probably the closest point, in the picture, but like, this picture doesn't, it's not good enough to like really get exactly what point is closest. So what we're going to do is the following. I identify x as the x coordinate of the point, y as the y coordinate of the point on this sideways half parabola on this curve, and then d is the distance between the point that we were just talking about here and then this point that was provided in the question. So you'll notice in a moment we're going to apply the distance formula between this point and that point. Now, traditionally we would say we are going to minimize this, and that would work to minimize d. However, you saw a moment ago that d has a square root symbol in it, and that makes things kind of awful. So it'll be much nicer. So it'll be nicer to minimize s, which is d squared instead, to minimize the square. So s is going to, in words, stand for the square of the distance. So you could minimize d, but we're going to minimize s instead. If you'd like to later, the picture that I already drew is available for you. We're not going to click on that right now, since you already saw a picture of this. Now we should take these 4 quantities up here and write any equations that will relate these things together. So first of all, there's the distance formula applied to this point and that point. It's the distance formula we just reviewed. If s is the square of the distance, then s is equal to d squared. And there's a way that the x and y coordinates here are related. They are points on the sideways half parabola, which is this curve. Therefore, that equation applies, right? This y equals root x applies. And so we have a total of 3 equations here, right? 3 equations. This first equation has 3 variables, right? D and x and y. This next one has 2 variables, and the last one has 2 variables. But so no, there isn't a single equation that has all the variables. But this is what we have, and now we should kind of work through these and solve for s, because that's the thing we're going to minimize. Apply some algebra. There's lots of different ways to do this. So one option is we can take this equation right here, and let's rewrite this down here with one little change. Notice where the y is, there's a root x instead. Okay, that substitution is because y is equal to root x. So that's a thing you can do. And then if you'd like to, this minus 0 can go away, right? Minus 0. And then the root and then the square undo each other. So it's still all inside the radical, but you should just have an x there. Now, again, I don't want to minimize d. We could, look, there's only one variable over here. And we could differentiate this, but it's just painful because of the square root sign. It could be, you can differentiate this, you just need the chain rule. It might be easier if we square both sides. So squaring the right side gets rid of the square root sign. Squaring the left side means we just write the square. And then the whole point is we can replace d squared with an s. And so all that happened here is d squared became an s. Now, I think it just looks much nicer to think about minimizing s instead of minimizing d, because d has this square root sign. It's just extra work. So we'll differentiate, and you've got two ways to do it. One option is you could take this, you could FOIL it out and differentiate. That works. Your answer may look a little different, but it'll be the you'll get the same final answer. I went ahead and applied the chain rule. So so this x squared as the exterior function. So 2 times the interior raised to the first power, and then this times 1 is from the chain rule. And then this plus sign is that plus sign, and then x differentiates to a 1. Now, this is the derivative, right, or the slope, so we should set this equal to 0 because we're trying to figure out, where is there a peak or where is there a valley. And in doing so, we don't need the times 1. Right? I put the times 1 there as a reminder of what's going on with the chain rule. So we'll set this equal to 0, 2 times quantity x minus 16 plus 1 equals 0. To solve this, I went ahead and subtracted 1 on both sides and divided by 2 on both sides. So you have x minus 16 is equal to negative 1/2. And then if you add 16 to both sides, 16, by the way, is 32 halves. So 32 halves minus a half is 31 halves. Okay, there's a lot of things on this slide. And now what I'd like to do is just keep some of this work and then this down here on the next slide. And maybe I'll pause and see if we're doing okay, first of all. Okay, so we've got this x value. Now we just need to know, what do we do with this x value? This x value is the critical number of s, right? It's like that special x value where something is going on if you were to graph s. So up here, I just copied stuff from the previous slide. It's all literally copied language with one exception. Here, I ran out of room on the last slide with showing all the work. Now I'm summarizing that when we set s prime equal to 0, we got x equals 31 over 2. But now the question is, what happens with this? In other words, there's this critical point, but is the value of s going to be big or small at this x value? Or in more technical language, are we going to have a local min or local max at this x value? We know that this is where the graph would level out. There's a peak or a valley, but what kind? So you could apply the first derivative test if you like, but I think generally speaking, the second derivative test tends to be nicer for these. This one's probably not so bad using the first derivative test, but what I'll do is take a look. Let's rewrite s prime first. So there's s prime up there, and this is still s prime. Right, so I just distribute the 2, so you have 2x minus 32 plus a 1, so that minus 32 plus 1 simplifies to a minus 31. Okay, there's s prime, and then to get s double prime, to differentiate, 2x differentiates to a 2, and a minus 31 differentiates to a 0. I just didn't write in a minus 0. Okay, so we have the second derivative, and I know this sounds strange because normally your second derivative function has the variable in it, and here we don't have the variable, but that's okay. We can just to illustrate a point and to be as consistent as possible with what we do all the time is we are going to plug in this x value, and you might say, where do we plug this x value in? The only place is right there. So don't replace the 2. That's sort of this kind of mistake that people make, overthinking things in algebra, just kind of making things up. It's everywhere you see an x, you replace with a 32 over 1. So when you do that, the only replacement is right there. Don't replace here. That's still just a 2. And so the point is, since the value of the second derivative is positive, s has a local minimum, right? So s has a local minimum because think about it. So s double prime positive, this is the thing that's going to correspond to s. S is concave up. Oh, what happened here? So if s is concave up, then that's going to lead to a local minimum. Okay, so we know that this value of x is good in the sense that it makes the value of s small, right? So it's making s small is good because we were trying to minimize s, but the thing is s was d squared. And so going back to this little experiment we did earlier with this collection of numbers that we sorted and squared or square rooted, so the x value that's making s smallest makes d smallest also. Okay, so this value of x is good, right? That's the value of x that we want. But now we need to go back and look at the question. It says find the point. And a point has an x coordinate and a y coordinate. So we need this and we need that. Need. We've got the x coordinate, it's right here, but we need the y coordinate. So how do we get this? How do we get the y coordinate? Well, that's where our other equations are helpful. So from knowing x equals 31 over 2, and the point is a point on the curve, so every point on the curve has to satisfy y equals root x. And I mean, if it doesn't satisfy this, it's just not on the curve. So this has to happen. So we should just now plug in this x value right in right there. And so then we get this. And this is, I think, why it's actually rather critical in the beginning of the process to write down what your variables mean. Because if you don't do that, it's really easy to get lost in the shuffle of what's going on. So sometimes people just want to write this without this part, but you'll get yourself in some trouble in the end of the process when you need to go back and answer your question. So it helps to write out what your variables really mean. I know that takes up extra time, but it's worth the investment of time to do that. So in the end, this x coordinate, this y coordinate, those numbers, we stick them in, x comma y with parentheses. So we have point notation here. That is the point on this curve that is closest to 16 comma 0. So we're done with the question. But as a bonus, what I just want to point out is that if the question said something different, so find the distance of the point on, like find the distance, like how far away is a point on the curve, just to ask a different question, if you need the value of d, well, that fortunately we know is this. Again, it goes back to what did all the variables mean. And so you can take this and just plug in for the x, plug in what we had over here, and for the y, plug in what we had right there. So I just plug those things in. And so that right here is the distance between the points. And that wasn't what was asked, but I'm just saying if the final question up here were a little different, you can answer that question as well. So once you kind of sort out whether you have the local min or local max, and you know the number corresponding to a certain variable, you can then go back to your other variables and get the values of whatever thing you need. And that point is what I'm trying to make here. You'll find this should be helpful, is that when you need to go back and answer whatever the original question was, you should look at which of your variables addresses that question. Now, if you wrote down a list of variables with clear explanations of what each means, here's the other thing. If you don't already have the numerical value of that variable, you probably already solved for that variable anyway. In fact, you had to have, because you solve for that variable to help get rid of that variable before differentiating. So use that version of the equation. It'll help. Or you could just rework it, like you can start from your original equations, but somewhere you probably already solved for that variable because you probably eliminated it because you chose, whichever algebra steps were most convenient for you. Overall, the big picture is this process of finding local or absolute mins or maxes. And just as a reminder from yesterday, what you need is the objective on one side, and then the other side of your equation should just have one variable. And then otherwise you need to do substitutions. For the rest of class, got 23 minutes or so, I would like to ask that you work on questions 13 and 14 from the sheet. So I'm going to pull up the sheet. And I want you to work on these because these are the ones that are most like the questions that the question we just did. Of course, I could go through another one, but the thing is, I think you should try this. There are things that I said that you're like, oh yeah, that makes sense, but you should try it out on your own. So I would please suggest that you look down here. Let me zoom in on them. And if you get stuck, unmute a mic. And we'll see if I can even do a message here. So folks, work on 13 or 14. I'll just have a quick announcement at the end. If you have any questions, you can unmute a mic and we can talk through a thing, or you can write up a chat, whether it's for the whole class to see or a private chat. I intentionally have moved my chat window to the other screen, so it's to screen 2, and what you always see being recorded is screen 1. So yeah, if no matter where you type, it will not appear as part of the recording. Mm-hmm. Okay. Okay. Strange. Okay, I can, yep, get rid of that. What is this? Oh, right. Okay, I can remove that and that and that. Let's do emails until I see a question. About 18 minutes. Let's make this more prominent. Like that. Okay. 1, 2, 3. Let's see. 3 emails. What is this? Oh, right, the online digest. I should read this real quick. As long as nobody has questions. Yeah. Okay. that's so many emails. Okay, okay, okay. Just keep swimming. I could read the committee things. That would be a good use of time right now. Okay, let's go back here. 12 minutes. Where's the freaking reading? Oh yeah, over here. Office.com. Guess I should read the minutes myself first, and then that, and that, and that. I need to minimize this if I'm going to see chats over here. There we go. Problem 13. Sorry, it was 5 minutes. Because I'm signed in two places. I didn't see the question on this screen, and I just realized that. So, question 13: how do you get rid of the y when you're finding the derivative for s? Yeah, good question. So I would. So keep in mind. I'll just I know you're asking the question privately, but I'm typing the answer to you while saying it to everyone. Keep in mind, y squared equals 2x. So you can um, solve for y in this, which looks painful because y equals plus or minus square root of 2x, or perhaps solve for x instead, meaning your variable in the end is y instead of x. Does that help? Yep. First read of API report for military science. Question to the other side of me. Would 217 be the point closest to the origin for question number 14? Ooh, so I don't remember off the top of my head, but I do have, and I have this just open in another tab here. Let's see, question 14. So, yeah, to answer your question, the x coordinate I got, of course, I could have an error, is right there where the hand, it's getting rid of it. It's where the hand symbol, if that appears, it's sort of like right in the middle of the screen. So my work is a little messy perhaps here, but I got negative and then 17 squared times 2 in the numerator over 2 plus 17 squared times 2 in the denominator. Maybe I'll scroll up so you could take a look at my work and see if that seems to jive for you. So let me know. I'll leave. Okay, cool. All right. See that comment? Yep, you're welcome. And then I don't see any response there, but okay. Yeah, I've got both my chat windows open. This is the problem of being signed in twice. So I'll just keep looking back and forth, and if I don't see questions, I guess I'll just keep reading something I have for a meeting tomorrow. And I still have 7 minutes. I will do just a quick round of announcements at the end. Oh, maybe I should, sorry, go back to just the tab that has the questions 13 and 14 again, though. And if you're done with those, like you can get the sheet and work on. I'll scroll up a little bit and just say, there's not really. Well, like question 6, for instance. Like yesterday I was saying work on 1 through 6, and I know there wasn't enough time for all of those. tab. Guess I should mute myself. There we go. Let's see. First read of API report for step. Ew. I'm not sure. Just do that. See if there's questions. We're doing well. Okay. All right. Just keep reading. Continue to develop. Curricular gaps, including. Middle school practice and pedagogy. Offerings in chemistry and history. We're close to the announcement mark. Maintain and continue to expand field and student teaching opportunities. Okay. Is that not happening? Huh. Okay. Interesting. Who would... Alright. Increase and broaden the participation in in-task assessment. Some areas to address 3-year report. Ooh. Okay. Let's see. Provide the latest version of the procedures for step promotion and retention, and include within report of the strengths and weaknesses. 2.5 minutes. Okay, we're at the 2-minute mark, so I'm just going to do a quick round of announcements here and say I knew it would come up at some point regarding like, wait, what's the final answer to this or that? So I have handwritten solutions here. They're not, um, they're not all that clean, but they're here, and I think you'd appreciate having these. So I'm assuming that's correct anyway. So I will post this online to Canvas right after stopping the recording and saving the recording. That I want to do that first in case the computer has an issue. So it'll take me a couple minutes to do that, but like maybe in about 10 minutes from now, Yeah, certainly within 10 minutes, you should see a copy of this PDF with worked out solutions. Now, that said, I wouldn't just look at these alone, right? Like you should really try the questions yourself in order to then look at these next. As far as just another kind of some quick things for announcements, then I'll just say, especially because it's time sensitive. Like today's a Tuesday, so please do the online quiz. Please keep up with the web work. And then I don't know if I mentioned it at the beginning of class or not, but right around 7:40 this morning, I made a survey available. It is optional, but I would love to really collect your feedback on just how things are going. I meant to do this earlier, but things have been just rather busy. Like everything takes quite a bit longer to do. But that said, like if a lot of people are having the same issues. I want to try to fix any major things that I can on my end to make this technologically work out better for you. So one of those things did come up already. Some people had trouble accessing one of the sites for videos, so I've actually been uploading videos to two places now. So there's a YouTube playlist. In any case, just if you would complete the survey, if you don't, I just have to sort of assume everything's going okay. But if there's something wrong, especially, please complain. And then I just need to see kind of what are the trends, like what are the things that are making things difficult for the most number of people, and then I'm going to just do my best to try to fix those things. Okay, so I will see you either in office hours later today or for class tomorrow.